Saxon Algebra 1, Lesson 35. We discuss factoring the greatest common factor and canceling. When we use the distributive property, we change an expression from a product to a sum. For example, the expression 2a parentheses x plus c tells us to multiply 2a by x plus c. The distributive property tells us that this product is the same as the sum 2ax plus 2ac, because we distribute the 2a. If we reverse the process, we can write the sum 2ax plus 2ac as the product 2a parentheses x plus c. Factoring is the process of writing an indicated sum as a product of factors. In this sense, it's the reverse of the distributive property. Example 1. Factor the greatest common factor of 2ax plus 2ac. That's the problem we just considered. The greatest common factor of the two terms is 2a. This will be one of the factors. We write it down and follow it with empty parentheses to indicate the other factor. Then we fill in the parentheses with terms so that 2a times each gives us 2ax plus 2ac. So the first term we need is an x, because then we have 2ax. And we have plus the second term, which is c, because then we have 2ac. Example 2. Factor the greatest common factor of this expression. Well, it's going to take some work to find the greatest common factor, so we write the expression in expanded form. It looks like this. Then we place the two sets of parentheses, and in the first set we need to put the greatest common factor. Let's see, each term contains two a's, so the greatest common factor has a squared. And the middle term contains only one x, so the greatest common factor has an x. And then each term contains two m's, so the greatest common factor has m squared. So our greatest common factor is a squared x m squared. Now we consider the second set of parentheses. We must place three terms in that second set so that the greatest common factor times each gives the original expression. So look at the first term of the original expression. We need to get a third x squared m squared. We already have a squared x m squared. So we are going to need another a to get a third and another x to get x squared. In other words, a squared xm squared times ax gives us that first term. So in the second set of parentheses, we need ax. Now look at the second term, a squared xm third. The greatest common factor already has a squared x and m squared in it. We just need another m. So the greatest common factor times m gives us that term, and therefore the middle term is m. And then we look at the last term of the original expression, which happens to be negative a fourth x third m squared. The greatest common factor has two a's. We're going to need two more a's. It has a single x. We're going to need two more x's. And it already has the m squared. So we can multiply the greatest common factor by negative a squared x squared, and that gives us the third term. So the third term inside the parentheses is negative a squared x squared. And there's our factorization. Do you see that? If we were to apply the distributive property to this factorization, we would get the original problem. So in effect, we're doing the distributive property backwards. Example 3. Factor this rather long expression. It only has 2 terms. Again, we will rewrite each of the terms in expanded form so we can identify the greatest common factor. We place 2 sets of parentheses, and then in the first set, we need to put the greatest common factor. Let's see, as far as the numerical part is concerned, each term has a 2, so 2 is part of the greatest common factor. Each term has at least 2 a's, so a squared is also part of the greatest common factor. Each term has at least 1 b, so b is part of the greatest common factor. And each term has 3 z's, so z third is part of the greatest common factor. Now we need to fill in the other parentheses so that when we multiply this out, we get the original problem. Let's see, we have 2a squared bz third. We want to end up with the first term as 4a third b fourth z third. So we need to multiply by 2 to make 4, and a to make a third, and b third to make b fourth. We don't need a z, we already have the z third. Now look at the last term of the original expression. We need to get 2a squared bz fourth. We already have the 2 and the a squared and the b, but we need another z. So we put z for the last term because that times the greatest common factor gives us our second term of the original problem. Example 4. Factor this expression. Again, we will write the terms in expanded form so we can identify the greatest common factor. Let's see, there's no numerical part of the greatest common factor. Let's put down our parentheses. But each of these terms has 2 m's in it, so m squared is part of the greatest common factor. And each term has a y. The last term does not have an x, so y is also part of the greatest common factor. So there's our greatest common factor. Now, for the second set of parentheses, we need to consider what do we multiply that greatest common factor by to get the terms of the original expression. To get 3m third xy squared, we need to multiply by 3mxy. Do you see that? M squared y times 3mxy gives us the 3m third xy squared. And then for the last term, the m squared y, we already have m squared y as the greatest common factor, but we have to multiply it by something added here, and the something is 1. Anything times 1 reproduces itself. So we place a 1 there, and this is the factored form of that expression. Now we consider canceling. When simplifying fractions, we have been canceling. For example, the fraction 24/40ths can be simplified by canceling 8ths in the numerator and denominator because 24/40ths is 8 times 3 over 8 times 5. And we cancel those 8ths to get 3/5. It's the same as dividing the top and bottom by 8. This works because 8 times 3 over 8 times 5 is the product of the two fractions 8/8 times 3/5, and 8/8 is 1. Likewise, we can cancel the 7's in 7 times 4 over 9 times 7 because 7 times 4 over 9 times 7 can be rewritten as 7 times 4 over 7 times 9. The denominator can be rewritten as 7 times 9. And then we have 7/7 times 4/9, and 7/7 is 1, and 1 times 4/9 is just 4/9. On the other hand, suppose we cancel the 7's in this expression, 7 plus 4 over 9 plus 7. It appears we get 4/9. This does not work, though, because 7 plus 4 over 9 plus 7 is 11/16, and 11/16 is no way equal to 4/9. So canceling works when everything is multiplied, but not when something is added or subtracted. Here's a question. Can you cancel the 7's in this expression? 7 parentheses 1 plus 4 over 9 times 7? The answer is yes, because the expression is the same as 7 times 5 over 9 times 7. We can get rid of that addition because of the parentheses there. And here it is in detail. It's equal to 7 times 5 over 9 times 7. Cancel the 7's, and we get 5/9. So in a case like this, we can cancel even though there is some addition, and the reason we can cancel is the addition is enclosed in parentheses. When variables are involved, we can likewise cancel provided the variables are factors of the numerator and denominator. The following examples illustrate this. Here we have a parentheses b plus c over ad. We can cancel the a's because of the parentheses around the b plus c. So we end up with b plus c over d. Another example, ab plus c over ad. This time we don't have the b plus c in parentheses, so the addition is messing things up. We cannot cancel here. You cannot cancel those a's. Do you see the difference between this and the previous problem? How about this one, ab over a parentheses b plus c? Yes, we can cancel the a's here because they are factors of the numerator and denominator. So this is equal to b over b plus c. But be careful, we cannot cancel those b's there because we have a sum in the denominator. How about this one, a parentheses b plus c over b parentheses b plus c? Can we cancel anything there? The b plus c is an entire factor. It's the same in the numerator as it is in the denominator, so we can cancel it, and this is equal to a over b. Here are some more examples. Simplify each fraction. 4 parentheses a minus 3 over 4. Can we cancel the 4's? The answer is yes, because they are factors of the numerator and denominator, and we end up with a minus 3 over 1, which is the same as a minus 3. Another example, 3 parentheses x minus 2 over x minus 2. Well, the x minus 2 can be looked at as an entire quantity, and it can be canceled. So we end up with 3 over 1, which of course is equal to 3. Another example, 3p plus 3 over 3. What can we do here? Well, the numerator is a sum. We don't have the product of two things. But what we can do is factor a 3 in the numerator. And that gives us 3 parentheses p plus 1 over 3. Now the 3 is a factor in the numerator, and therefore it can be canceled. And that leaves us p plus 1 over 1, which is p plus 1. Here's a similar problem, 3x over 3x minus 9x squared. Because we have a difference in the denominator, we cannot cancel directly, but we can factor the denominator. We can factor out a 3x in the denominator. That gives us 3x times parentheses 1 minus 3x. Now we can cancel those 3x's in the numerator and denominator. And that leaves us with 1 over 1 minus 3x. One more example. 5x minus 25x squared over 5xy. Again, we have to factor. We factor the numerator. We can factor out a 5x there. We get 5x parentheses 1 minus 5x over 5xy. Then the 5x's in numerator and denominator can be canceled. And we're left with 1 minus 5x over y. So the secret to canceling is, yes, you can cancel provided everything is multiplied. And to make everything multiplied, you might have to do some factoring. This is the end of lesson 35. Your assignment, problem set 35 on pages 144 and 145 of your book.